I will start my video.
So, hello everyone. It is 7 p.m. Thank you for tuning in to On Beyond Prolog, the first, I think, online edition of the Munich Lambda Meetup. So, thank you very much, Annie, for coming to, well, not actually coming, but like for joining in online to deliver this talk. And the topic is basically, yeah, as the title already says, On Beyond Prolog. Um, Prolog has kind of the idea that you can embed languages in there and can do stuff with them. And Annie is well known for doing fun stuff with Prolog, and I hope she's going to share some insight from that now.
Hi, so this is Prolog. This is the Prolog we learned in school. Many of us, something about discovering who your aunt's, mother's, niece's nephew was, and people are often left wondering what's beyond it. I'm going to show you a whole bunch of things that are beyond it, and we're going to, and very much feel free in the chat to ask questions and probe for details. I am going to go through these pretty rapidly. It's the smorgasbord of fun things in Prolog. So this is Prolog, but gosh, this is also Prolog. This is a complete user registration and identity management login package for Prolog. So you can write real, honest to goodness stuff. I can't think of too many things that are more boring than and work a day than getting logged in and getting your account set up. But we can extend Prolog, and this is a very traditional extension to Prolog. It's the definite clause grammar. Now, I will say many of my examples I'm going to show are partial. I basically put what would fit on one slide. This is a kind of a taste of things. Definite clause grammars let you define the syntax of a language in a Bacchus-Nauer format-like way, and then use that as a parser or a generator for the language. So here's a little bit of simplified version of English, and we could then determine whether input strings were in this or generate them. This is another extension here. HTML is actually DCG itself, which takes as an argument a Prolog term and interprets that as and assembles ordinary HTML out of it. So this bit of code would make an H1 tag followed by a P tag with the contents of A and B in them respectively. This is fine. This is a very nice way to do web programming, as long as you have lots of dynamic content. But it's inconvenient if you're inserting Google Analytics code they give you, or a PayPal button, or the web designer sent you a bunch of HTML, and you already have the HTML in normal form. So we can extend Prolog using Haskell-style quasi-quoter. Quasi-quoters have been with us for a while, And when the Prolog reader reads this code in, the area, highlighted area in yellow is going to be converted into the previous form. So, so you can see this is about as far as you get with most other languages. Quasi-quoters, in Scala and Haskell, and then that's it. But Prolog keeps going. Prolog is not an OO language, but it contains a small IDE. This window I've got up here is the editor from the built-in IDE. And when you're thinking, oh God, must have sucked to write an IDE for Prolog, because like that'd be an ideal fit for OO, and Prolog's not OO. Well, nope. We just changed Prolog to an OO language for a bit. You'll note that the area highlighted in yellow is PCE begin class, and yes, this defines a class called Emacs. The little editor is called PCE Emacs, and then when you look down below, this actually doesn't look that much like Prolog beyond very superficially. There's no neck operator, and there's a bunch of send messages and so on. So, gosh, we can, the way this is implemented is that we put that PCE begin class is actually arbitrary Prolog code executed as the reader reads in the file. So PCE begin class gives us installs a hook into the reader and alters the code as it's coming in. So what the downstream compiler sees is Prolog. State's always a horror. So let's extend Prolog. There's a system called constraint handling rules. It's actually available in a number of languages, but one of them that's very commonly used in is Prolog. Most functional languages sort of stick their heads in the sand and say, no state, no state, no state, and hand you a state monad. And that's admittedly, it gets rid of the state for the mathematicians, but it's not always not always what we needed. Constraint handling rules do something a little more engaged and proactive. The CHR has a constraint store and constraints. You drop things into the store, and there are rules that make them transform. So this one does mixing paint colors. So if I drop magenta into the store, it's there. I have magenta in the store. I drop yellow into the store, and the last line fires, and the magenta and the yellow are removed and replaced with red. So that's CHR. There's many cool things you can do with CHR. Here's another large application that was mostly CHR, and teams and SWI-Prolog organizes teams to enter the Ludum Dare game jam. Our entry was this last time was a silly little game about a pig and a wolf. And the wolf chases the pig, and you have to draw houses for the pig to live in. and then the wolf, of course, blows down the house, and you have to draw another one. The recognition algorithm for recognizing freely drawn child houses was written in about 6 hours during the jam by myself. So we have various ways of reasoning. This is deduction. No, it is. If you make a fire here, you will burn down the house. And with deduction, we deduce truths from other truths via rules. If we know there is a fire here, and that building a fire here will burn down the house, then we're going to burn down the house. This is Charles Sanders Peirce, 1870. His second rule, his second type is induction. And every time I made a fire in my living room, the house burned down. Aha! The next time I make a fire in my living room, the house will burn down too. This is going from a collection of prior events to finding new rules. And the last is abduction. We're going to go from events and rules to prior possible facts. The house could have burnt down for other reasons, but perhaps my cousin again. So, what's this look like in Prolog? Deduction's easy in Prolog. It's kind of what Prolog does. If there's a fire in the living room, the house burns. If is reversed in Prolog. This is the Aleph inductive logic system. We want to do induction. We want to, let's go back and look at Charles Sanders Peirce. This is, I have a bunch of prior cases, and I am going to deduce a rule from them. So, this is induction. I have a bunch of prior cases, and I have a definition of grandparent that depends on parent. And parent, in this case, is not defined. But we ask Aleph to patch this hole, and it figures out that a parent is either a father or a mother. This can be very useful for attempting to find rules in a system. Why am I missing the abduction case? Hang on. Aha, okay. All right. So, Prolog is closed world reasoning, which means anything I don't know, I assume is false. But that's not always the best, the correct assumption. Suppose I want to know if the grass is wet, and I haven't looked outside today. I don't know. I sleep soundly. Did it rain last night? It's hard to encode such abductive reasoning in Prolog itself. But Henning Christiansen at Roskilde University in Denmark has built a Prolog that handles abduction. Or I should say, and I should say it as a kind of an aside, that building a prologue to do a specific kind of reasoning is a fairly common thing. So here we use Hyprolog and we say, the grass is wet, and it responds, maybe it rained last night, or maybe the sprinkler was on.
Okay, so FedEx, so planning is an application that, or is an area of computing that was initially came out of Prolog and has a long history of involvement with Prolog, although computationally it's getting so large, the problems are getting so large that they're now implemented in low-level languages. So Federal Express ships 14 million kilograms of freight every day. They do not fly fixed route or schedules, but rather replan their flight based on their pilots, their planes' locations, whether their pilots need to get home, and where the boxes need to go. So planning is a special case of abduction. Planning is, it's always combining atomic actions, this would be your basic facts, and finding basic facts that combine together to make what you need done, the thing you wish to prove. And the rules for such actions are actually defined in a standardized language called PDDL, the Planning Domain Definition Language. One of the commonly used planners is LPGTD, which is part of the LPG series. So that's planning. Nobody has questions. I'm getting no feedback. It's very weird.
So nobody has asked questions so far, but I will encourage everyone again to please ask questions if you
Okay.
have.
All right. Okay. I'm just going to keep going. So this is an interesting application of planning, is to generate stories. Many of these systems descend from an old system called Tailspin. So we're back to Prolog because it was written in Prolog. So any fiction writer will tell you the way you make a story is that you have things go wrong. You have some characters, they make a plan, they go out to execute the plan, and things go wrong. When they go wrong, they then have to figure out how to achieve either their original goal or some more urgent goal from the new state. So, for example, if you plan to go on vacation, you may say, well, I'll get my tickets, I'll go to the airport, I'll get on a plane, I'll lay on the beach, I'll come back. Well, that's fine. But if you get to the, I'm on the plane and the plane crashes in the Amazon rainforest and you now are stuck with no preparation in the middle of the Amazon rainforest, then your goal no longer is to get on vacation, it's to stay alive. And so you replan from your current state, and then you do this again. You go through this loop again. You replan from your current state, you go back to 2, execute the plan, and more things go wrong in the typical story. So interestingly, this makes you can write pretty bad fiction this way. And in fact, we did a prologue class a couple of years ago, and this was the class project, was to write one of these. So I wrote a tailspin implementation that tells stories about my pet robot snail, Pomatia. So I thought I'd read you just a little bit of one of the stories to get the sense. One day, Pomatia was invited to tea at the mushrooms beyond the pond. Froggy lived there and always gave such grand tea parties. Pomatia had a particular hard berry they liked to use as a ball. Pomatia decided to take the ball with them. They crawled along the brick path that wound through the garden. The friends played with Pomatia's ball. Suddenly, old Mrs. Cratchit, who owned the garden, appeared. All the creatures were afraid of Mrs. Cratchit, who threw stones at them. They crawled along to a nice ornamental pond with a little fountain and lily pads that Froggy loved. Mrs. Cratchit went back inside to watch her soap opera. The garden residents sighed with relief. They crawled along to a large group of mushrooms under a willow tree where Mr. Froggy lived. And so the story goes on. So, okay, this is Prolog. Prolog has a pub sub system, where that's useful for kind of agent-oriented programming. I can register to listen to the orcs, and then at the interactor, Prolog's version of a REPL, I can say broadcast orc hi, and the listener says an orc says hi. Okay, that's semi-interesting. Let's get more interesting. I can start up Prolog on one machine.
Annie, short interruption.
Yes.
We have a question.
Okay.
So the question is whether tailspin is written in Prolog.
Yes. Yes. It's. I tell you what. After my talk, I will. Before I get off, I will find the URL to the Git repository, to the GitHub repository. Okay.
Great. Okay.
But yes, it was definitely written in Prolog, SWI-Prolog.
Okay.
Okay. So we're at distributed Prolog. So I've got my same listener, but here I've loaded, and that's running on the green machine. We imagine we have two computers here on a LAN, and one is green and one is red. And then I go to the red machine and I load library UDP broadcast, and I do more or less the same broadcast, but I say to send it to the UDP. And it shows up on the other one, which is kind of nifty. So all of a sudden we've got distributed agent programming with only a few characters changed. Here's another way to distribute Prolog. Once again, we have the green machine and the red machine. The green machine is running the Pension server, which is part of SWI-Prolog. And the Pension server allows you to call the machine up over HTTP and ask for a Pension's sub VM, basically get your own VM on that machine that lives within the server's VM. And here we have defined this little predicate, my member. A member will tell you the various members of the various entries of a list. And so my member is just a copy of it that just calls the original. So I go to my second machine and I do Penguin RPC call, and the URL of the Penguin machine, which could be anywhere, and I send it a call to my member, and it comes back with A, B, or C. And in fact, I could have just called member or any of the other library predicates. I can't call anything dangerous like halt, which is the thing that stops the Prolog virtual machine. But and how do we get away with this? Why isn't this a huge security nightmare? Well, basically, the Penguin server looks at the code and does code analysis and says, yeah, that's not going to call anything dangerous. So using our enhanced ability to analyze our own code for practical uses.
Henning, I have another question from Hans about pensions.
Okay.
And the question is there any current development in Penguin, for example, other possible clients?
I don't know of anyone writing a Penguin's client at the moment. However, there are already Penguin's clients for for like a large number of languages. Not all of them, certainly. I don't think there's a Haskell Penguin client or a Go Penguin client, but there's one for Java, Ruby, Node. You can call them from the browser, which is really cool, from JavaScript from the browser. Python, and I'm forgetting somebody. There's one more out there, but my brain is gapping on it.
All right, thanks.
So, yeah, I honestly, they're easy to write. If your language, if you want a Penguin client in your language, I suggest you look at those Java Penguins in Similarity on GitHub, and we will make certain and you can copy that and have yourself a client in a pretty short time. Java Penguins and Tailspin. Sorry, writing down what all I've promised to give people. And okay, well, you can do other things with a program than just execute it. So A implies B is great in some absolutely logical world, but things in the real world are rarely this certain. I get in my car to drive to the store. It's nice. You can say, Annie got in her car, therefore she's going to the store. And there is indeed a high probability that I arrive at the store. But I might have an accident, hopefully not severe. I might see a friend. We end up hanging out. It gets late. The store is closed. I'll go another day, blah, blah. Causal chains like this can become quite long and complicated. And so we often find it difficult to reason about these long chains of causality that have probability in them. CP-Lent is a system by Fabrizio Griguzzi, the University of Ferrara, who that allows us to model this sort of world. And what CP-Lint does is it gives us different Prolog programs and the probability that this is the logical model of the world for this time. So here I've got, A implies B 80%. Then I can combine these probabilities and get net probabilities of 3 different Prolog programs. How tall is my mother? And now I've asked an interactive question. Somebody's gonna have to type it. Give me an answer. Anybody on chat want to guess how tall my mother is? Am I still here?
Yeah, you're still here. The YouTube stream is slightly delayed, so we're going to pause for a moment.
Oh, okay. All right.
Let me check the stream just for a second.
I forgot about the YouTube delay.
Okay, so the question has arrived now in the chat. So we'll see if somebody's up to answer this. So someone said 170 centimeters. 1 meter 70.
I've done a pretty careful check all over the internet that I can find. And I can't find my mother's height anywhere online. So, which is why I use this problem. And I'm kind of guessing that nobody here knows my mother except me. So we don't exactly know my mother's height. But it's also not true that we know nothing about my mother's height. And Prolog itself models variables as either we know the value definitely and exactly, or we know nothing about the variable. Constraint logic programming over finite domains says, well, hang on. What if we allowed saying things like, my mother's height is between 50, between 1 meter and 2 meters. That's a good guess. I think we can safely say that. My mother's height is not negative. It's not a list of 3 strings. It's a number. It's a number that is probably between 1 and 2 meters. Yeah. So, well, my father was 5'8". Forgive me, I'm an American. And my mother was shorter than my father. Now we can constrain the value further. And in fact, eventually we could get down to where there's only one answer, and then we would know my mother's height. Yeah. So this is a small program that figures out train schedules that involve one layover. That is just to keep the sample example short. And there's a bunch of trains. They start at, I have some stations that are numbered in sequence, and I have a station we go from, the station we go to, the time we depart, and the time we arrive. And So our voyage is going to consist of 3 stations, and the 3 stations are going to be a voyage from A to B, B to C, and then C to D. So those have to match, and we have to, the arrival of the departure time for the second train has to be greater than the arrival time of the first train, so we can catch that train. And of course, I'm sorry, there's 2 layovers in this, and each of the elements then must correspond to an actual train that exists. So this is a constraint program. This can be a very powerful way to program. Okay. We can ask other questions. We can ask questions like, what values can X take on? Well, X just reports the members of the list, so this one's trivial. It could be A, B, or C. But if we had a complicated program, this could be really hard to determine. So, a little more on beyond prologue, and yes, we're getting towards the end. This is OWL, the web ontology language. Tim Berners-Lee's other idea. The web is great for humans, but what about computers? Well, people post data on the web, and everybody has their different idea of what format to paste it in. And it's not even really that like one person posts CVS files and the other person exposes an HTTP endpoint. That's actually not the most painful part of it. The most painful part of it is that you never know what the values really mean. So Tim Berners-Lee said, oh, well, what if you could, if I made a format for data in triples, subject, a verb, and an object, and the triple, and then that middle verb position, we had a language for describing what the heck that thing means in relationship to the other verbs. So we could say, oh, what big Co calls employee name, small Co calls name. And those are actually the same thing. So at that point, though, you have to have some way of reasoning, and that lands us back in Prolog land. Well, all this stuff's neat, but I want to make my own. So how do I do that? Well, I can make syntactic changes. That is, I basically just want to spit out Prolog, but I want to write it differently.
We have another question before you continue.
Okay.
Related to the past few slides. The question is from Pavel, and the question is how many facts could SWI-Prolog potentially operate on, and are there strategies of lazy loading or something like that to, for example, handle time series which contain a lot of facts?
Contained what? To handle something that contained a lot of facts. What was the
time series? Time series.
Oh, time series. Prolog facts are not quite stored as efficiently as Java objects, but they're pretty close. Prolog can easily handle a very large number of facts. I used to work for a Prolog shop, and we did analysis of large satellite images in Prolog. It really made the machines grind, but we did it. You know, it's not out of line with the size of data storage in other languages. Particularly if you are cognizant of what you're doing. For example, if you have large numbers of strings that you suspect are going to all be unique, don't store them as atoms and make them be in the atom table. If you think many of them will be similar, then do store them as atoms. You know, and that sort of thing. If you truly just have a large table of data, there's a system called Record that allows you to get a in-memory store of raw data, and just essentially make yourself a database table in memory. And
Okay.
that's the solution for doing very large things, not to store them as objects.
Okay, perfect. And one more remark. Someone said that the slide you showed about the RDF processing, it kind of looks a little bit like Sparkle.
That's deliberate and a very useful property. You are right. It definitely looks like Sparkle. And this is valid SWI-Prolog code. I think I can claim that SWI-Prolog supports semantic web better than any other language. There is a Sparkle server that's part of the semantic web support that comes with SWI-Prolog. So if you want to stand up a Sparkle server for your Prolog back system, all you have to do is basically load a library and tell it where the HTTP is.
Okay, thanks.
Okay, I'm going to start over this make your own. So, we have, so I want to make my own. This looks cool. Gosh, I can make all kinds of things in here. So how do I go about altering Prolog? Well, I might just want to write something, for example, in a form that is more natural to some domain specialists that I work with, or that I already have a lot of material in that format, or or just this is the traditional format for this material. I don't want to make my musicians deal with Prolog looking stuff. Or I might be making what are actually seemingly semantic changes because I'm just transforming the form. That's basically what you're doing with most of XPCE, for example. So how can we do this? Well, what are our hooks in? Well, one is that any Prolog compound term can be declared as an operator. Arity 0, 1, or 2. This operator, actually Arity 1 or 2. And these operators can then be written in fix. So by using operator precedence and declaring operators, you can do an amazing amount of pretty clever parsing, and I've seen some amazing stuff done that way. You can use a thing called term expansion to insert arbitrary Prolog code, excuse me, into the reader. So let's say you have an enormous Prolog program and you need in some complicated way to either add or not add an extra argument every place you called some commonly called thing throughout the program. Oh, what a pain, you know. Maybe you can write something that's clever enough to refactor it automatically. Maybe, but it looks undoubtful, you know, looks doubtful. So, but I could get into the compilation stream, and if I see it, if I see this going on in a certain context, then I can just add my extra argument. Another thing you can do is you can just flat out write your own parser. It's pretty trivial in a language with DCGs because you know, Backus-Nauer format non-terminal definition is a fundamental operator in the language. Parsing is just like addition. So, and finally, and then, you know, if I have a parser, if I don't want to suck that in from a different file, I can just stick it in the middle of the Prolog code by means of the quasi-quoter. But syntactic changes are the minor leagues. We can also do semantic changes. One thing we can do is make them look like syntactic changes by completely changing what's going on with the as the code's compiled and passing it some kind of meta interpreter. We could also just write a meta interpreter and pass stuff to that. You can write Prolog in about a page. So that's a very powerful thing to do, is make your own specialized Prolog by just writing it in Prolog. And finally, the system is extremely hooky. Unification is sort of Prolog's version of assignment, and Prolog programmers would throw their shoes at me if they heard me. But when that unification happens, you can hook that. And in fact, that's how CLPFD happens, is that it's on the attribute hook. So Prolog to infinity and beyond. We are having a big online Prolog class, and I will put the URL to sign up for that. I will pass that to Lars to stick on the YouTube as well. So the big Prolog class is about to start the enrollment process. So get yourself on the list now. Okay. All right. Lars, I'm going to stop my screen sharing and go back to video.
Yes, thank you very much, Annie.
Yeah.
I have one more question, which I have buffered from before, and there's a few more questions rolling into chat, so we'll just go through them one by one.
Okay.
So the first question is, could Tailspin be used to create game content, like procedural content?
It is similar narrative generation systems. Tailspin is kind of the version of these systems, which are now called narrative generation. And Dr. Chris Martin at University of North Carolina operates the Poem Lab, where they specialized in narrative generation. And it's not only can be, but definitely is used in many games.
Okay.
So kind of procedural generation. We've all played computer games, and if you've been doing it long enough, you remember characters who always said the same stupid thing. And these days, they're getting much smarter, and that's because they're beginning to use this procedural content generation.
So we have a few more questions, I think.
Okay, great.
So one question that has been asked a few times is about the course you mentioned, the upcoming course, and if there's a beginner track or an advanced track, or like how what kind of tracks there are.
It's going to be in two pieces, run one after the other. There will be a absolute start from zero track or class, the basic prologue class. And then when we finish that, right afterwards, we'll start the advanced class. So, and we're charging a little bit for the class, and we even have a bundle deal if you get both of them. At least that's what Ian tells me. It's not my department.
Okay, so next question is basically about all the things that you have talked so far, like Tailspin and Cpillant and all the other stuff. Could you please elaborate if this is dependent on a particular Prolog implementation, or if this is portable across implementations?
Well, I mentioned Hyprolog at one point. Of course, you have to have Hyprolog to do that. And but the rest of them, I'm pretty much talking about SWI-Prolog. Quite a few of these are implemented on other systems. I know that the constraint logic programming stuff, for example, is pretty widely available on other systems. But some of them are just on SWI-Prolog.
Okay. So
Prolog is it's kind of in the nature of Prolog that it's never going to be that well standardized, just because it's so flexible. It's like precision machining Jello, you know.
Okay, and then final question for now. Does the SWI-Prolog team use Prolog itself for validation, like theorem proving purposes?
No, basically. The SWI-Prolog team is Jan and me doing kind of DevRel stuff, and some folks who make contributions, you know, who send us PRs, and one nice thing about our background and coming out of academia is that a large number of people have done their PhDs on SWI-Prolog, including, I believe, Dr. Hupel. Did you do your PhD on SWI-Prolog?
I used the theorem prover, but not SWI-Prolog.
Okay, well, yeah, I mean, for that kind of work, frankly, dedicated theorem provers are better for doing dedicated theorem proving. But yeah, you know, if you go back, for example, to Lifshitz's original paper on answer set programming, you'll find it's in Prolog. So Prolog is kind of the language under all of this.
Okay, we got one more question. It's great that people are so active around here. So the question is, if I have a constraint problem, like a scheduling problem, for example, why would I reach for Prolog over a language that's tailored to constraint modeling, like Z3, for example?
Good question. And you might be better in your constraint modeling language, but for example, if you are trying to build, if the reason you're doing constraints is that you have some kind of little specialized CAD system, CAD systems are often full of constraint systems, then you're going to have to do an awful lot of just general programming as well. And so Prolog's a natural thing to reach for. Yes, if you have a single problem like that, yeah, you might be better off in your specialized tool.
All right. Well, I think that's it. If you could, I think we took a note during the talk about the tailspin implementation, I guess. It would be great.
Yes, and Java Pensions and the Prolog class.
Yeah, so
I will get you.
Yeah, I've already linked the Prolog, the Pensions implementation in the chat. And
the Prolog class.
The Prolog class, not yet. No. Can you send me the link? I will paste it to the chat.
So, okay, just hang on for just a moment and I will put that in. Lars, I see you on the IRC. I can paste it there.
Okay. All right, while we're doing this, there's another question that just came in. The question is, there's a terminus DB, which is great. And is there a new age of Prolog now?
There is a new age of Prolog. Bodil Stock, types gadfly and pure script person, and conference organizer, says that it's her mission this year to make Prolog mainstream. So, and she's not primarily a Prolog person, so she's so that's a good sign. Okay, I've pasted the link to the class, and what was the other one you wanted?
I think I have a link. Please check the channel if it's the correct one.
That's Tailspin. That looks like the right one. And then Java Pensions, which is on the Simularity.
Okay, I think someone said that you should be. Someone is asking for you to give updates on Twitter on the Prolog class, which I think you're going to do anyway.
I update at least once a day.
I think we're good to go. There are no further questions.
Okay, great. So,
it remains to say thank you, Annie, for giving the talk. Thank you all for tuning in. We've had
thanks everybody. This has been great fun.
We had a total of 28 simultaneous streamers.
Wow.
So that's really nice. I hope you will excuse the few technical flaws. I will give my best to publish a cleaned up video without the gaps in between. So please stay tuned on our Twitter account, and please also join the Prolog account on Freenode. It's #Prolog on Freenode. Follow Annie on Twitter, follow the SWI account on Twitter, and people on the stream are saying thanks also. So seems like people like the talk. And I'm going to end the stream now. See you sometime.
Okay, great. Thanks.